In this video, we'll look at the dehydration of an alcohol. So dehydration, when most people hear that word, they think about losing water. And that is what takes place during a dehydration reaction. So sometimes you may simply see that alcohol and you'll see an arrow such as this. This tells you that the reaction is proceeding to form the product. But during that process, if you notice how that arrow kind of goes up with water at the end, that's letting you know that water is being released. So technically you can see this reaction arrow in the dehydration. You can also see it represented in condensation, because both of these you're going to have water as a product. So let's look at what takes place and how to predict the product of a dehydration reaction. And so I'll redraw this compound, make it a little bigger. I'm going to actually show the bond between that oxygen and hydrogen. So writing it as OH is the same thing as saying I have a bond between that oxygen and hydrogen. So what happens during a dehydration is that you end up losing water. And so again, when thinking about the water molecule in these reactions, think about it as HOH. Something is losing H, something is losing OH. And so when that takes place, the result is the formation of a double bond. And so we have to look at where that double bond is going to form. And so you always want to identify the carbon atom where your alcohol group is attached, because that carbon will be involved in the formation of that double bond, of that alkene. And so we know that this carbon atom is going to be involved. From there, you want to look at the carbon atoms right next to it. So in this case, I have a secondary alcohol that I'm starting with. So I have to look at those two carbon atoms around my alcoholic carbon, because I technically have two possible choices for which carbon atoms will be involved in the formation of that alkene. And so since we have two possible choices, I'll just redraw this so that we can go through and look at those two choices. So in order for dehydration to occur, we have to lose water. We can already see the OH, so technically I didn't have to actually show that bond because I can see my OH. So I know that I'm going to be losing that OH. The carbon where your alcohol functional group is always going to lose the OH. But then one of the carbon atoms next to it would then lose a hydrogen. And so if we look at carbon 1, we see that carbon 1 only has one bond, so we know that this carbon has 3 hydrogen atoms. If we look at carbon 3, it has 2 bonds, so we know that it has 2 hydrogen atoms. So for my two possible choices, carbon 1 can lose a hydrogen here. Carbon 2 will lose the OH. That gives me my water. For the second molecule, the hydrogen can be removed from carbon 3, and again the OH removed from my functional group. So when either of those occur, we can see how the water is formed. But again, as we've seen with other reactions, we almost have this half of a bond here and then half of a bond there. What ends up happening is these two atoms. So this carbon still had that half a bond, this carbon still had a half of a bond. So what ends up happening is that each carbon takes that half of a bond and ends up forming a double bond. It doesn't matter whether you show that extra bond above or below, as long as it's between those two carbon atoms. The same thing here. So now we're saying carbon 2 and 3. They're going to take their half of bonds each, their half bonds, to form a whole bond. So we have two possible choices. If we go with the method of this first structure, we end up with 1 butene. If we use the second structure, we end up with 2 butene. The way I have it drawn is trans 2-butene, but I'm only concerned about the 1 butene versus 2 butene. These are two different compounds. Which one would we see more of? So when trying to determine which would represent the major product, we can predict the major product of a dehydration reaction by locating that alcoholic carbon, looking at the carbon atoms that are attached to it. primary alcohols, there's only one to look at. Secondary alcohols, as what we have here, we had 2 carbon atoms we could look at. A tertiary alcohol, we would have 3 to look at. But I'll get to tertiary alcohols in just a minute. Once we determine the carbon atoms that are involved, in order to predict your major product, look to see which carbon that's directly bonded to that alcoholic carbon. Look to see which carbon atom has the fewest number of hydrogen. So in our 2 examples, carbon 1 had 3 hydrogen. Carbon 3 only had 2 hydrogen. Once you identify which carbon that's directly attached to that alcoholic carbon, which carbon had the fewest number of hydrogen, that alkene that forms using that carbon would represent your major product. And so in this example, because we had carbon 3, which had more hydrogen, versus carbon 2, which had fewer hydrogen, carbon 2 would give us our major product. So while we may see a mixture of both compounds, we would see more of the 2-butene than we would the 1-butene. So let's look at another one. So let's say we had this. And we were doing this hydration reaction, or dehydration reaction. So now we'll look at the type of alcohol. We have our alcoholic carbon. We have 1, 2, 3 carbon atoms attached. So now we have a tertiary alcohol. So if we look at the carbon atoms around that alcoholic carbon, so I'll just go ahead and redraw it. So I have my alcoholic carbon here. 3 carbon atoms attached. The carbon to the left only has 1 bond, so therefore it has 3 hydrogen. The carbon above has 1 bond, so it has 3 hydrogen. The carbon to the right has 2 bonds, so it has 2 hydrogen. So again, to predict the major product, we want to go with the carbon that had fewer number of hydrogen, which would be this carbon. And so what ends up happening during this process, one of those hydrogen would be removed from that carbon along with our alcohol functional group. So remember, this is how we'll end up with our water, because we'll lose one of those hydrogen. So now instead of 2, we'll have 1 hydrogen. And so when we redraw that product, we can't change the number of carbon. We still have the same number of carbon, but now we have a double bond between carbon 2, which was my alcoholic carbon, and carbon 3, which had a fewer number of hydrogen. So now we've gone from a tertiary alcohol to an alkene. And so we could do the same thing with a primary alcohol. Primary alcohols, you won't have as many options. So if I had this as my alcohol, so it's primary because this represents that alcoholic carbon. It only has 1 carbon atom attached. And so that 1 carbon atom attached has 3 hydrogen. But I don't have anything to compare it to. So I know that I'm going to lose a hydrogen from that carbon, carbon 2. I'm going to lose my OH from my alcohol functional group. It's going to simply become this. I'm going to just go ahead and write in the C's just so that no one's thinking this is just an equal sign that I drew. So we've lost that OH. We've lost one of the hydrogen. This carbon had 2 bonds, so there were initially 2 hydrogen. This carbon had 1 bond, so there were initially 3 hydrogen. Now both carbon atoms have exactly 2 bonds. So each has 2 hydrogen. So the carbon to the left simply lost the hydrogen, so it went from 3 to 2. The carbon to the right, it didn't lose any hydrogen, but instead it lost the OH. So in addition to this alkene, we also have water. So for your dehydration reaction, you're simply starting with an alcohol and you're going to an alkene. The alkene that is formed as your major product is formed as a result of that double bond forming between the alcoholic carbon and the carbon that is adjacent, so right next to it, that has the fewest number of hydrogen.